When de Broglie suggested that electrons, or matter in general, can have both a wave and a particle function, he really opened up a lot of research opportunities. Niels Bohr got a cohort of scientists together in Copenhagen and tried to come up with a theory for why electrons behave the way they do by looking at electrons as particles. And his theories led to the Bohr model that you studied, which we've now come to say is wrong. Because while Bohr's theories worked really well with hydrogen with only one electron, when you started adding more electrons, the variables became so complicated that his theories fell apart completely. Another problem with Bohr's models of electrons in steady, stable orbits was that it was proven that you couldn't determine how fast an electron was moving and where its exact position was at the same time. This is called the Heisenberg uncertainty principle. I can tell you how fast an electron is moving, or I can tell you where it is, but I cannot tell you both with an equal amount of with definite certainty. The more you know about one, the less you'll know about the other. So while Bohr was working with his team, another scientist by the name of Erwin Schrödinger worked independently, and rather than focus on the electron as a particle, he focused on it as a wave function. So let's review a little bit about waves. In a standing wave, which is a wave in which both ends are attached to something or have a node, if you were to pluck, quote unquote, a string like this, like say it was a musical instrument, you could end up with a couple different standing waves. You could end up with one that only had a half a wavelength from one node to another. You could end up with one that had a full wavelength, both a crest and a trough, or you could end up with some that have multiples of those half wavelengths. If you have multiple waves overlapping one another, they can form what's called constructive or destructive interference. Constructive interference would be if I had another line here that went along with this wavelength, and they would add up and the amplitude would increase. Destructive interference would be these dotted lines, which run opposite the wavelengths, and they would diminish the amplitude. And in fact, these dotted lines would perfectly annihilate both of these all of these waves. Schrödinger found that only certain waves could fit into the proposed orbits where electrons were known to be found. Meaning that the energy in an electron, because these waves symbolize the movement of an electron, and the number of waves you could fit into that orbit corresponded to the energy level of those electrons. The types of standing waves where only certain allowed wave functions could fit around the orbits, Schrödinger symbolized with the Greek letter psi, which is a set of wave function coordinates x, y, and z. Because in order to find something in three-dimensional space, you need a location on the y, x, and z axis. Z being going into the screen and going out of the screen. If you take the square of psi, you have the probability of finding an electron in a particular point in space. And it's a ratio of point A compared to point B, psi of A compared to psi of B. So let's say the ratio is 100 to 1. That means you have 100 times more chance of finding an electron at point A than you do at point B. You can call this, it's also called the intensity of probability, or the electron density. They're all synonymous terms. If you were to create a probability distribution of where an electron has the greatest chance of being found, it would look like this, where the darkest shading is where there's the highest probability of finding an electron, And the farther out you go, the less shading there is, therefore the less chance there is of finding an electron. This is called an electron density map, or electron probability, or electron density. They all mean the same thing. When we say orbital, this is the image that we're talking about. On a graph, it might look like this, where the distance from the nucleus, you have the greatest chance of finding an electron near the nucleus because nucleus is positively charged, electrons are negatively charged. So as you move away from the nucleus, there's less of those electrons you have a less chance of finding electrons further from the nucleus. Waves that are for allowed energy state are what we call orbitals. If you were to graph the radial probability of finding an electron further and further from the nucleus, the graph would look like this as you move away from the nucleus versus the probability of finding an electron. So even though as you're moving out, your probability, as you move out, while probability is greatest near the electron, we're taking the radial probability, so we're taking in more positions the further out we go. So while probability is greatest near the electron, or near the nucleus, while probability is increases up to a point, eventually it will begin to decrease as you move further and further away from the nucleus. Notice, though, that the probability is an asymptote. It will never reach zero. So you can never say there's no chance an electron will be all the way out here. You can say there's a very minuscule probability that it will be, but you'll never say there is no chance. There's no probability that far away from the nucleus, because really we have no idea. Which is why the shape of an atom is often a blurred image. Ooh, and I'm apparently moving this for no reason. Because we can say there's a very high chance of finding an electron near the nucleus, but as we move out, there's less and less of a chance of an electron being there. As chemists, we agree that the size of an orbital is defined as the area where you have a 90% chance of finding an electron. After that 90% chance, 89% chance in dropping is where we cut off. So the size of an orbital is defined as the area where you have a 90% chance of finding an electron. If all of this quantum mechanics stuff is making your head explode, do not worry. You will very rarely be tested on anything this complicated or in depth. The real stuff will come. This is just the background information, so you can understand it better when it comes up later. Quantum numbers and atomic orbitals. This will look very confusing to your friends, but if you really want to impress them, you can tell them with some certainty an electron's, in quotes, address and what state it's in, or what spin it has developed. And it's going to look very confusing because we symbolize it with a whole bunch of crazy letters. But it's really just an address. In a three-dimensional world, which is what you live in, electrons can be up, down, left, right, front, and back. And you need to be able to find them on a three-dimensional plane. So we'll need an x, y, z coordinate, and then spin simply has to do with magnetism, and we'll be getting into that in a few minutes. The first part of the address is n, or the principal quantum number, principal energy level. These are the same term. It's a number between 1 and infinity, and it's the distance the electron is from the nucleus. It describes the orbital size, or diameter. If you remember doing electron configuration in baby chem, when you said 1s, anything in 1s, any electron in 1s had a principal energy level of 1. 2s would be the electrons would have a principal quantum number of 2, sorry. The next part of an electron's address, in quotation marks, is its angular momentum, which we symbolize with a cursive L. Because electrons within an energy level can be grouped into shells or subshells. We sometimes call them sublevels. Sorry, not sublevels, sublevels. And each one has its own certain wave shape because the angular momentum corresponds to a shape. Now the principal energy level, or N, limits what L can be. L can be any number from 0 up to n minus 1. So if you have a principal energy level of 2, then L can be from 0 to 1. And the number of possible sublevels, therefore, for if n equals 2, it can be 0 or 1, so the number of possible sublevels is 2. So the number of possible sublevels, or the number of possible L's, is equal to n. What can those n's be labeled as? Anything from 0 to n minus 1. Angular momentum, or L, corresponds to the shape. The S sublevel is spherical. S stands for sharp. But in baby chem, I probably told you S stands for spherical. I lied. S stands for sharp. The higher the energy level, the higher the principal quantum number, the larger that particular shape, that wave shape. The P sublevel has a dumbbell or peanut-looking shape, which can be oriented upon the 3 different axes of 3-dimensional space. You can have a P sub x, which is oriented around the x-axis, a P sub y, which is oriented along the y-axis, and a P sub z, which is oriented on the z-axis. The D sublevel has 5 unique shapes. You can have the first 4 all look like clovers, all oriented around different axes or in between. The last one is what we call a torus, which I think is spelled T-A-R-U-S. And lastly, the F sublevel, not lastly, because you can go past F, you just start alphabetically after that, G, H, I, J. But the last sublevel that we can actually at this time make a picture for is the F sublevel, and they're crazy. No one will ever ask you to describe the shape of an F sublevel, because I don't even know where to begin. Also, the F sublevel are really small, and they're never used in bonding. So not until you're a major in chemistry, maybe doing analytical chemistry, that you'll even discuss the F sublevel again, at least in a geometric setting. The final piece of the address, besides the spin, we'll get to that later, is the magnetic quantum number. And it's simply the assigned blanks, quote unquote, in the orbital notation, with 0 being the middle, and then from negative L to positive L. So if we were going to do the orbital notation of sulfur, the first thing we would have to do is the electron configuration. Now, if what I'm about to do is going to blow your mind, there is a video coming for that. So go to that video, and then it will make sense. But really quickly, the electron configuration of sulfur, I pulled the periodic table, is 1s2, 2s2, 2p6, 3s2, 3p1, 2, 3, 4, 3p4. So when you write it out, just write it out like that. Now, each quantum number gets the L that goes next to it in its alpha form, or its letter form. So if L is 0, so 1, n minus 1, so 1 minus 1 is 0, so that's why that's an S. another 0 is an s, a p is a 1, and there are no d's in this, or f's or g's. The orbital notation would be 1s, and then the number line you would go over, it started at 0, since you only have an s, there's only one line. 2s, again, it's an s, there's 0, no other lines. P, you'd have 3 lines from negative L to positive L. So this would be the orbital notation. Now if I wanted to give the address of the final electron, the 16th electron in sulfur, it would be first the address is always set up, the principal quantum number, L, M sub L, and then the spin. So the principal quantum number is 3, because that final electron is found in the third. The sub-level is P, and P corresponds to what number? That's right, 1. The magnetic quantum number, where is that last electron found? It's found in the -1 orbital. So this is -1. And lastly is the spin, which is symbolized by M sub S. So we have to talk now about a little bit about magnetism. There are 3 situations in which something is magnetic. It can be diamagnetic, paramagnetic, or a ferromagnetic. Diamagnetic is not magnetic at all. And you can remember this because magnetism dies. In fact, diamagnetic materials are slightly repelled by magnetic fields. And these occur when all electrons are paired, meaning every up has a down, because they'll cancel each other out. A substance that is paramagnetic is actually attracted to a magnetic field, but will lose its magnetism when it is removed from that field. And chemically, this occurs when you have one or more unpaired electrons. Unpaired, paramagnetic. But most of the magnets you probably come in contact with, or that you know of as being magnetic, are ferromagnetic, which are magnetic after they've been introduced to a magnetic field. This can occur when clusters of atoms have their unpaired electrons within a cluster. And the clusters are more or less aligned, the substance acts as a magnet. If you drop the magnet, though, you can rattle those clusters and make it unmagnetized. All of these are explained by electron spin. Each electron has a magnetic field with both a north and a south pole. Electron spin is quantized, meaning that in a magnetic field, only 2 orientations of it are possible. +1/2 and -1/2. The up is +1/2, the down is -1/2. Just accept that they're 1/2. Don't ask me why, it's just because for Schrodinger's equations to work out, up is +1/2, down is -1/2. Also, in order for the equations to work out, in 1925, Wolfgang Pauli stated that no 2 electrons can have the same 4 quantum numbers, meaning that no 2 electrons can both be up or down. They have to cancel each other out. Meaning that you cannot have 2 up arrows, or you cannot have 2 electrons both spinning up in the same sublevel. So the final quantum number for our sulfur example would be, since this final electron is down, we would say it is -1/2. Now it's important to note that it really doesn't matter what you put for that final quantum number, as long as it's either positive or minus -1/2, because the AP exam does not care if you start with up arrows or down arrows, because in reality that's all it really matters. As long as you have some number, and then plus or minus 1/2, you have to pick one. You can't put plus minus. you can get the full credit.